For 25 years, one of the most precisely measured numbers in all of physics refused to match its own prediction. The number describes something almost absurdly small: how a subatomic particle called a muon wobbles when placed in a magnetic field. Physicists can predict that wobble to 11 decimal places using the Standard Model, the equations that describe every known particle and force in the universe. And for a quarter of a century, the actual measured wobble kept coming out slightly different from the prediction. Not by a lot, but consistently and precisely enough. That kind of persistent gap in physics means one of two things. Either there are particles or forces in the universe we haven't discovered yet, subtly tugging on the muon in ways our equations don't account for. Or somewhere in an extraordinarily difficult calculation, something is wrong. In 2021, the tension reached 4.2 sigma, a statistical confidence just short of the 5 sigma threshold physicists require to call something a discovery. It looked, for a moment, like physicists might be standing at the edge of the first confirmed crack in the Standard Model in decades. Then, the theory changed, and the crack didn't close. It moved somewhere else entirely. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. To understand the muon anomaly, you first need to understand what a G factor is. A muon is a subatomic particle, a heavier cousin of the electron, that behaves like a tiny spinning magnet. The strength of that magnetism relative to its spin is described by a number called its G factor. The simplest version of quantum theory, the Dirac equation, predicts that G should equal exactly 2. It doesn't, quite. Real particles interact constantly with a churning quantum vacuum, full of virtual particles flickering in and out of existence. And those interactions add tiny correction terms that nudge G slightly above 2. The size of that nudge, G minus 2 divided by 2, is called the muon's anomalous magnetic moment, or muon G2 for short. It's a number physicists can calculate using the full Standard Model with extraordinary precision, because every known particle and force contributes a specific, computable correction. That makes muon G2 one of the most sensitive tests available for finding physics beyond the Standard Model. If an undiscovered particle exists, something too heavy or too weakly interacting to have been directly produced and detected at a collider, it would still leave a fingerprint here as an extra tiny correction to the muon's wobble that the known Standard Model particles alone can't account for. Predict the number as precisely as possible. Measure the number as precisely as possible. Compare. That's the entire experiment in principle. In practice, both halves of that comparison turned out to be brutally difficult. The story starts at Brookhaven National Laboratory on Long Island in the late 1990s and early 2000s. Brookhaven's muon G2 experiment used a specially built magnetic storage ring, a 45-foot diameter circular magnet, engineered with extraordinary uniformity, to trap muons and measure their wobble directly. When the final Brookhaven results were published in 2006, they showed a discrepancy from the theoretical prediction of about 3.7 standard deviations. Significant, suggestive, but not conclusive enough on its own to claim a discovery. The experiment couldn't easily be improved at Brookhaven. Reducing the uncertainty further would have required either more data or a redesigned setup, and the lab didn't have the resources to pursue it at the time. So the entire 50-foot magnetic ring, an object so precisely constructed that reproducing it from scratch would have been extraordinarily expensive, was physically transported from Long Island to Fermilab, near Chicago, in 2013. Not disassembled and rebuilt, moved essentially intact by barge down the Atlantic coast, around Florida, up the Mississippi and Illinois rivers, then trucked the final stretch. An enormous, delicate object moved 1,000 miles to avoid remanufacturing a magnet no one wanted to risk building twice. The upgraded Fermilab Muon G2 experiment began taking data in 2018, aiming for a measurement precise enough to settle, one way or another, whether the Brookhaven discrepancy was real. In April 2021, Fermilab released its first result, and it confirmed Brookhaven. The new measurement, taken with completely different equipment, operated by a new generation of physicists, landed close to the original Brookhaven value, independent confirmation that the anomaly wasn't some quirk specific to one experimental setup. When the Fermilab and Brookhaven results were combined, the overall discrepancy between measurement and theoretical prediction reached 4.2 standard deviations. For context, particle physicists generally require 5 standard deviations, a 1 in 3.5 million chance of the result being a statistical fluke, before declaring an official discovery. That's the same threshold used to confirm the Higgs boson in 2012. At 4.2 sigma, the Muon G-2 anomaly was tantalizingly close, but not there yet. Still, the announcement generated genuine excitement across particle physics. If the discrepancy held up and grew with more data, it would represent the first confirmed evidence of physics beyond the standard model from a laboratory experiment, something the field had been searching for without success since the Higgs boson's discovery nearly a decade earlier. Every major particle collider search since then had come back with the same frustrating result. The standard model, checked and rechecked, kept holding. Muon G2 looked for a moment like the exception. If the discrepancy were confirmed as real new physics, what would it actually mean? It would mean an undiscovered particle or force is contributing to the muon's magnetic behavior, something not accounted for anywhere in the standard model. Physicists have no shortage of candidate theories that could produce exactly this kind of effect. Supersymmetric particles, hypothetical heavier partners to every known particle, proposed decades ago to solve several other outstanding problems in physics, could contribute the right kind of correction if they exist at accessible energy scales. So could leptoquarks, hypothetical particles that would let quarks and leptons interact directly. So could dark photons, a proposed new force-carrying particle connected to dark matter. The appeal of Muon G2 as a search tool is that it doesn't require directly producing and detecting a new particle at a collider, something enormously difficult if the particle is too heavy or interacts too weakly. It only requires that particle to exist somewhere in the quantum vacuum, contributing its tiny correction to the muon's wobble, even if we can't make or catch the particle directly. That's what made the 2021 result so significant. A confirmed 5 sigma discrepancy wouldn't just be an interesting number, it would be a signpost, telling physicists roughly what energy scale and what kind of new particle to go looking for next. Here's where the story takes its first real turn, and it happens on the theory side, not the experimental side. Calculating the standard model's predicted value for Muon G2 requires accounting for contributions from every fundamental force, including the strong nuclear force, the force that binds quarks together inside protons and neutrons. That particular contribution, called the hadronic vacuum polarization, is by far the hardest part of the calculation, and there are 2 independent methods for estimating it. The first is data-driven, using real experimental measurements of electron-positron collisions producing hadrons, then using established physics relationships to convert those measurements into the needed correction. The second is Lattice QCD, a from-scratch computational method that simulates the strong force directly on a supercomputer, without relying on collider data at all. For years, these 2 methods roughly agreed, and the data-driven approach was treated as the more reliable of the 2. It's what produced the theoretical prediction that the Brookhaven and Fermilab measurements disagreed with. But starting in 2020, a major Lattice QCD calculation from a group known as BMW produced a noticeably different result, one that, if correct, would shrink the gap between theory and experiment considerably, weakening the case for new physics. Two respected methods for calculating the same number. Two different answers. And the entire strength of the Muon G2 anomaly rested on which one was right. The disagreement got messier before it got clearer. In 2023, a Russian collaboration called CMD3 released a new measurement of the exact electron-positron collision process the data-driven calculation depends on. Their result was significantly larger than every previous measurement of the same process, including the result from their own predecessor experiment, CMD2, which had helped establish the original data-driven prediction in the first place. That created a genuine crisis inside the small community of physicists who specialize in this calculation. If the CMD3 measurement was correct, the data-driven prediction needed to be revised upward, and doing so would bring the theoretical prediction much closer to the experimental measurement, again shrinking the anomaly. If CMD3 was flawed instead, the original tension would stand. Physicists spent years scrutinizing both the older measurements and the new CMD3 results in extraordinary detail, looking for a systematic error that could explain the discrepancy between the datasets. As of the mid-2020s, no clear source of the difference has been identified. The data-driven camp is, at the technical level, still not fully self-consistent. What is clear is that the once solid theoretical prediction, the number that made the original anomaly look so compelling, turned out to be built on a calculation with real, unresolved internal disagreement. While the data-driven camp wrestled with its own internal contradiction, the Lattice QCD approach kept improving and kept landing closer to the experimental measurement. Multiple independent lattice groups, using different computational techniques and cross-checking each other's work, converged on results broadly consistent with the original 2020 BMW calculation. In 2025, the International Muon G2 Theory Initiative, the collaboration of theorists tasked with producing a consensus standard model prediction, adopted a new, consolidated lattice-based average. That new prediction came out to a value of 116,592,033 in the relevant units, with an uncertainty of about 530 parts per billion. Compared against the experimental measurement, the difference was small enough to be statistically consistent with no disagreement at all between the standard model and the measured muon wobble. In June 2025, Fermilab released its third and final measurement, the most precise ever recorded, at 127 parts per billion, exceeding the experiment's original design goal. It agreed closely with both of its own earlier results and with the older Brookhaven measurement. The experimental side of the Muon G2 story had become remarkably stable and consistent. It was the theoretical side that had shifted, and in shifting, it had quietly closed most of the gap that made the anomaly look like new physics in the first place. By early 2026, the picture had sharpened further. An international team led by the BMW collaboration published a new hybrid calculation in Nature, combining refined lattice simulations with a small, carefully chosen slice of experimental data from a region where the older collider measurements do agree with each other. Their result achieved a precision of under 0.5% on the most difficult part of the calculation, and it landed close to both the earlier lattice results and the experimental measurement. Combined with Fermilab's final, most precise measurement, the overall picture as it stands now is this. Using the lattice-based theoretical prediction, the Muon G2 anomaly that generated so much excitement in 2021 has largely deflated. The gap that once suggested new, undiscovered physics can now be explained using only known standard model particles and forces, provided the lattice calculation, rather than the traditional data-driven calculation, is the correct one. But that provided is doing real work. The lattice prediction still directly clashes with decades of accumulated collider data used in the data-driven method. A conflict between two theoretical approaches that has not been resolved, only clarified. The muon's wobble didn't turn out to be a clean discovery of new physics. It also didn't turn out to be a clean non-discovery. It became a dispute about which of two extraordinarily difficult calculations to trust. There's a broader lesson buried in the muon G2 story, one that applies well beyond this one measurement. A persistent gap between theory and experiment doesn't automatically mean new physics. Sometimes it means the theoretical side of the comparison, built from independent calculations, each involving their own extraordinarily difficult technical challenges, simply hadn't converged yet. The muon G2 anomaly looked for years like one of the most promising cracks in the standard model in a generation. As the theoretical calculations matured and cross-checked each other, most of that crack closed, not because the experiment was wrong, but because the prediction it was being compared against turned out to be less certain than it first appeared. This distinguishes muon G2 from the Hubble tension, another tension between two precise measurements covered in an earlier episode of this series. In the Hubble tension, both sides of the disagreement are direct measurements, made with increasingly precise instruments that have refused to converge no matter how carefully the data is checked. In muon G2, one side of the comparison was always a theoretical calculation, and it's the calculation, not a physical measurement, that shifted. That distinction matters for how seriously physicists take each anomaly today. The Hubble tension remains one of the most actively pursued open problems in cosmology. The muon G2 anomaly, once considered comparably significant, is now viewed by much of the field as most likely resolved, pending final agreement on which theoretical method is correct. For 25 years, the muon's tiny magnetic wobble looked like a message from undiscovered physics, a persistent, precisely measured gap between prediction and reality that refused to close. Two independent experiments at two different laboratories using two entirely different generations of equipment confirmed the exact same wobble. The problem was never really the measurement. It was the other half of the comparison, a theoretical calculation involving the strong nuclear force so difficult that two legitimate independent methods for solving it produced two different answers, and only one of them could be right. As of the most recent data, the balance has shifted toward the calculation that closes the gap, rather than the one that opened it. If that holds, the most promising hint of new physics in a generation will have turned out to be a very hard math problem, not a new particle. But the two theoretical methods still don't agree with each other, and until they do, the door, even if it's mostly closed, isn't fully shut. Do you think there's still new physics hiding in the muon's wobble? Leave your take in the comments, and subscribe, because the next classified file goes up in a week.